This is Onufallar Joy, and today I'm going to present the paper named Attention is All You Need. This paper introduced the transformer architecture, which is one of the most important breakthroughs in modern machine learning. Nowadays, we all know about transformer. In fact, many modern models like language model, translation model, or translation system, and chat-based AI system are based on this idea. So in this presentation, I'll explain the idea of this paper in a simple and intuitive way. So let us first understand the problem this paper is trying to solve. Before transformer, most sequence models, like those models used to work with sequence, were based on a recurrent neural network or RNN. So RNN process data sequentially, meaning one word at a time. For example, in a sentence, the model processes the first word, then the second word, then the third word. This creates a major limitation because we cannot process everything at the same time. So even if we have powerful GPUs, we cannot fully use parallel computation, which makes training slow. So that was a great problem actually. Another major issue is vanishing gradient problem. So as we know, the neural networks train using gradients, but in case of RNN, these gradients travel back through many time steps. As they move back, they become smaller and weaker. This is called vanishing gradient problem. We can understand this using a simple analogy, like passing a message through many people. Each time it passed, the message becomes weaker and less accurate. Because of this, the model struggles to remember earlier information in a long sentence. So this leads to a problem called long-range dependency. That means understanding relationship between words that are far apart in a sentence was very problematic with these models like RNNs. So, for example, connecting the subject at the beginning of a sentence with a verb at the end was very difficult. So the goal is to design a model that can understand sequence without sequential processing. Now, as we have seen the problems, now let's see about the motivation uh, behind this work. So modern GPU are designed for parallel computation, right? So meaning they can do many operations at the same time. But RNN forces us to process data one step at a time, which is actually waste of this power. For example, imagine solving 10 problems. Sequential method means solving one problem at a time and then the next one, then the next one, this way. In case of parallel method means solving all the problem at once. So clearly parallel is much faster. Another motivation is understanding the global context. In language, any word can depend on any other word even if they are far apart. So we need a model that can look at the entire sentence at once and learn the relationship between them, like between two words, any two words, directly. To understand the improvement, let's briefly look at the previous approaches. First, we have a recurrent neural network. RNN actually maintain a hidden state which carries information from one word to the next word. But this creates a problem. As the sequence become longer, the information stored become less reliable because of vanishing gradients, as we have known earlier. The model gradually forgets the earlier information. Now we also have convolution neural networks. CNN processes data faster than RNN and can capture local patterns. However, to understand the relationship between distinct words, CNN may need many layers. Right, like CNN can easily understand local patterns, but to understand a global relationship or like understand the relationship between two distant words, CNN needs many layers. So this make them inefficient for long range dependencies. So both the approaches like CNN and RNN has a like sort of trade-off. RNN are slow and forgetful. CNN are faster but still struggle with long dependencies or long distance relationship. This is why researchers need a completely new approach. Now comes the main idea of this paper. The transformer removes recurrence completely and introduce a thing called self-attention. So self-attention means each word in a sentence look at all other words and decides which one are important. So instead of processing words step by step, the model processes the entire sentence at once. For example, we can give an example if we consider a sentence, the animal did not cross the street because it was too tired. Now, if we see this it is definitely refers to the animal, not the street, right? So it obviously refers the animal, not the street. Self-attention allow the model to directly learn this relationship. Using those earlier models like RNN, it was like hard as we have seen already the vanishing gradient problem. Long like if two words are in a distance like are apart from each other, then it was very hard to capture their relationship. But in self attention, we can see the whole input together, like whole sentence together, and we can easily calculate or measure the connection or relationship between any two words. So every word builds its meaning by looking at the full context of the sentence. This is the key actually. This is the key breakthrough. No recurrence, no sequential processing, only attention. Now let's talk about the architecture. The transformer actually uses an encoder decoder structure. The encoder reads the input sequence and convert it into a meaningful representation. So if we see the architectural diagram, then we can see the left side the block is actually referring encoder, and the right one is referring decoder. So as we have already said, like encoder read the input sequence and converts it to a meaningful representation, and decoder generates the output sequence step by step using this representation. So formally we can see like encoder we first we input our text into the encoder. Actually we didn't directly input our text to the encoder. We first tokenize it and like numerically represent it. We make vector embeddings and then input it into the encoder model. So the decoder actually here the decoder use the output of the encoder and generate like new sequence or new token, as we can see step by step, like one token at a time. So inside both encoder and decoder we have multiple layers. Each layer contains three main components. First is multi-headed attention. So instead of using a single attention mechanism, the model uses multiple attention heads. So we will understand what is a multiple attention head a little later. So each head focuses on different type of relationship in the sentence. So for example, one may focus on grammar, another may focus on meaning, another on the like world relationship. So second part of the layer of a transformer is feed-forward neural network, which process the information further. And third is a residual connection, which helps stabilizing training by allowing information to skip layer. We can think the multi-head attention like multiple expert analyzing the same sentence from a different perspective. Now let's get more clear. So as we have seen the architecture of the transformer, now let's see what is like attention. So in the left side, we can see like attention is a multiplication of three vectors actually, q, k, and v. So we can think like we have a sequence of inputs. Let's say we have sequence x1, x2 up to xn of inputs, and this is a transformer layer. So in the transformer layer, first we have, as we said, like the attention, self attention, self attention layer. So what is actually does? We have three weight vectors. We can see like WQ, WK, and WV, and we have a representation for these like input tokens, like vector embeddings, we can say. So we multiply that embeddings with that weight vector, and we get three new vectors for, or matrix you can say, for each input token, like Q, K, and V for each input token. So we get QKV for x1, we also get QKV for x2, we also get QKV for xn for all. Like all are different though. Now attention layer has two main parts. First of all, the attention layer do relevant scoring. Now, what does relevant scoring mean? It actually mean like how much relevance this portion of the input has with any other portion, let's say xk. So how much relevance these two input token has. Now, for calculating that, we apply this multiplication like q and k, like we apply q and the transformation like transpose of k. For example, like we have a q vector and a k vector, like the transpose of k, and we multiply this. This signifies how much like relationship these two input token has. So this is the query of, like this is the we can think is like this is the query of x1, and this is the key of x k. This is the key of xk. So key of xk, and we can think this as query of x1. So if we multiply them, we got a value. That value represent like how much connection they have. So in the same way, we multiply the query with all the all the key, like key of all other tokens, with like k1, k2, like all other tokens, and we got a score, and that score signifies how much connection x1 have with all other input tokens. And lastly, we how we get our final thing. Then we, for example, this is a1 and this is a2. Then we get our final thing by combining a1 into v1 plus a2 into v2 and so on. All right. So this is about a single attention head. Now what is multi-head attention? As we have already said, like we have multiple layers doing the same thing of operation. It can be considered as like different people viewing the same thing from different perspective. And finally, we concat all those layers using any other weight matrix, which can be like WH, or we can name something else, and that's also learnable. So we combine output from all those layers and concat them. So in this way, what we have done, we have actually uh, do relevance scoring, and then finally we combine those information, and we have already calculated the relationship between any two words in the input sequence or token. So now let's understand the core idea behind attention. We have already seen what attention is and how it's being calculated. So these are the formal representation of all those equations. So as we have seen, each word is represented using three vectors: query, key, and value. The query represent what word is looking for. So query represent basically it's like a question. So and the key represent what information a word contains, and the value represent the actual content. So the model compares query of one word with key of all other words. As we can see here, this gives a score that shows how important each word is, as we have said already. Then this score are used to compute the weighted sum of values. We have seen that. So final output is a combination of most relevant words. So now, as we have seen, all the other tokens or all other words will get a relevant score with the current word being processed. So we will combine all of their values, like it's like a weighted sum. So the word or the token is most important will get most weight, more weight, and the less important one will get less weight. So although the equation looks complex, the model learns what to focus on and how much attention to give. So we can see the equation here. So like the numerator term actually, as we have seen here, how much focus should a word A give to other word B? That represent that. And the denominator term, like root decay, is just a scale factor to keep numbers manageable during the training. And we have already told about like multi-headed attention, like we have multiple layer of attention doing all the same kind of thing, and we have like the matrix, like the weight matrix, WQ, WK, and WV for all the layers, and they might be like separate or the same. It depends. Like in case of this paper, they like introduced a different weight for different like attention head, but later we have seen like grouped query or like multi-query system, which we can discuss maybe later. So now see the result. The result of this paper are very impressive. The transformer achieved state-of-the-art performance in machine translation tasks. So it outperforms previous models like RNN and CNN, as we can see from the result. But more importantly, it was much faster. Like it was much faster to train. This is because it allow fully parallel processing. As we have seen, in the attention layer we have multiple heads, so every head can be computed parallelly, and um, in a single attention head, every token can be processed parallelly too, like as they doesn't depend on the completion of other token. So in a single head also the computation can be parallel. So this actually improves the training time. Instead of taking weeks, training could be done in just a few days. This efficiency made it practical for large-scale machine learning system. Let's see what are the strengths and limitation of this model. So one major strength is parallelization, as we have already seen, which makes the training very fast. Another strength is ability to capture the long-range dependencies effectively. So as we are now like computing the attention for all the full sentence altogether, and there is no point like vanishing gradient or something like that. So we can capture the long range dependencies very effectively. Also, attention can be visualized, which makes the model more interpretable. However, there are some limitations. The model does not naturally understand the word order, like which word come first and which one come later. But in case of natural language, this is very important, right? Like the order of the words. This convey a lot of things, it contains a lot of information. So we use something called positional encoding to solve this problem. Another limitation is that the computation grow quadratically with sequence length. This means longer sequence require like much more computation. Now, to conclude, the transformer introduced a completely new way of processing sequence using attention only. It removed recurrence and convolution and achieved better performance with fast training. This paper had a huge impact on machine learning. Today, most modern AI systems, including language models, vision models, and audio models, are based on this idea. So, this paper is not just an improvement, it's a fundamental shift in machine learning. And that is why the title is very meaningful. Attention is all you need. Thank you.